We're going to start this video with talking about photochemical smog. Smog is a mixture of smoke, fog, and sulfur compounds. And all of them together, we sort of make this word smog. So if we look at this top reaction, if you look while I sort of talk it through, it's the daytime reaction. And so if we think about daytime, we have sunlight. And so nitrogen oxides are up, VOCs are down, or volatile organic compounds are down, and that makes ozone. At night, the nitrogen oxide is still present, but the ozone plus the nitrogen oxide yields oxygen plus nitrogen dioxide. So when petrochemicals and volatile organic compounds are limited, the cycle takes place on a daily basis, and there's low smog. The temperature is important. Volatile organic compounds naturally and anthropogenic increase evaporation. So our VOCs, things whether they're natural or anthropogenic, increase with higher temperatures. We also have higher electric consumption, which is going to put more of that in the air. So when our volatile organic compounds are present, so this is looking at our second one here, when volatile organic compounds are present, they combine with that nitrogen oxide, which means that that nitrogen monoxide is not available to break down the ozone by recombining with it. And that's why we end up with a daytime accumulation in urban areas. So when we look at this regular reaction, we have this nitrogen dioxide. It'll be from nitrogen monoxide plus oxygen, and then we'll have an oxygen and O2 will combine and we'll make some ozone, but ozone then will combine with the nitrogen monoxide to put off oxygen and then O2, and this cycle just continues. We fluctuate between this NO2 and this ozone with our intermediary of nitrogen oxide. When the volatile organic compounds become involved, our nitrogen dioxide starts the chain. We have the same thing. The nitrogen monoxide combines with oxygen, and oxygen plus the O2 leads us to ozone. So we go through these steps here. But instead of cycling back, the volatile organic compounds that we've put into the air combine with that nitrogen monoxide, pull it out, and therefore that ozone can't break down. So here, the ozone is formed, the ozone breaks down. Ozone is formed, ozone breaks down. Here, ozone is formed, ozone can't break down because the volatile organic compounds are getting in the way. So that's the important difference right there, and how we are impacting that. Here's sort of another view of what's going on. You have pollutions, reactions in the atmosphere that's leading to that photochemical smog. Thermal inversions. Thermal inversion is when you have a warm layer of air that's covering cold, dense air, and that warm layer traps emissions that then can accumulate beneath it. It's common in cities, and it can sort of magnify other forms of pollution. Acid deposition, which deposition refers to rain or snow or however that is coming down. Regular acid rain occurs from carbon dioxide. Carbon dioxide in the atmosphere lowers the pH from 7, which is neutral, to 5.6, which is acidic. True acid rain is anything that's lower than 5.6. Of course, we have carbon dioxide in the atmosphere. We know it's going to be there from exhaling, and that automatically brings our water level pH down to 5.6. Our NOx and our SOx, when we have nitrogen oxides and sulfur oxides, they're released into the atmosphere, and in the presence of oxygen and water, these primary pollutants of the nitrogen oxides and sulfur dioxides become secondary pollutants. So they become nitric acid and sulfuric acid. They become washed out of the air in rain and snow, and they have been reduced in the United States due to the Clean Air Act amendment in 90 and 95. But pollution can move from the U.S. to Canada and between England and Germany and the Netherlands. The effects, it affects materials, it affects agriculture, it affects aquatic and terrestrial habitats. Directly, it's the lowering of pH of pond water, the greatest effect on aquatic ecosystems. We learned amphibians survive at 6.5, a pH of 6.5, but they start to have problems at 5.5 to 6. Below 5, a pH of 5, most salamanders will die. So acid can also mobilize metals like aluminum and mercury. And the human skin can protect us, but this can harm structures and statues and monuments and buildings. And hydrogen will react readily with limestone and marble, which is calcium carbonate. And there are some of the effects that I just talked about. It lowers the pH of lake water, decreases species diversity, mobilizes metals, becomes part of the food web. Human health is more affected by the precursors than the actual acid rain. Our skin does a pretty good job of protecting us from acid rain. And then damaging statues, monuments, and buildings. Ways to prevent air pollution. This is sort of a little summary of them, and then we'll go through them in more deep. Control of sulfur and nitrogen oxides. One of them is the fluidized bed combustion, which removes sulfur dioxide from coal exhaust during combustion. What about NOx? We have lower burn temperatures, the amount of oxygen. Catalytic converters in vehicles have been a huge reason that we've controlled emissions. Removing sulfur dioxide from coal exhaust during combustion by fluidized bed combustion. So we have granulated coal burned by calcium carbonate to reduce that sulfur oxides. The calcium carbonate produces calcium sulfate, and then we can take that calcium sulfate and use it to make sheetrock. And then just to finish up nitrogen oxides, they are produced in all combustion. They burn at lower temperatures with less oxygen and form less, but incomplete combustion will put more other particulate matter and carbon monoxide into the air. Nitrogen oxides are lowered from automobiles due to the catalytic converters, like I just mentioned. And now we no longer, lead isn't good for catalytic converters, so that allowed us to not put lead in our gasoline. So looking at particulate matter, it's the most common means of pollution control. And the simplest removal is gravitational settling. Ash can go to the landfill. The ash may have metals, and all forms of removing of particulate matter use energy. So you, in some ways, are generating more pollution. A baghouse filter is the first way. It's just essentially a big fabric bag that the smoke and gases can pass through, but not the particulate matter. It can remove almost all of the particulate matter if we use a baghouse filter. Another one is called Electrostatic Precipitator. It has a positive side and a negative side, and the particulate matter is attracted to the positive or negative charge. And then the clean air moves out, and we can just clean those plates off. And then so you can see the pictures here. If you see the picture without the electrostatic precipitator on, you can see those 3 smokestacks burning. And then we can go ahead and look with it on how much of that particulate matter is removed. It's pretty impressive. And then particulate matter scrubbers. A scrubber uses water and air and forms sort of a liquid sludge with the particles and reduces sulfur dioxide too. It has been used to reduce pollution dramatically. Smog is hard to overcome because the main component is ozone, which is a secondary pollutant. So we need to work on reducing the primary pollutants, usually directed at the reduction of VOx. And most recently, there's a focus on reducing NOx emissions. Innovative pollution control. China, Mexico, England has undergone some innovative and controversial measures to reduce smog. Measures to reduce smog include 1, reduce the amount of gasoline that is spilled. 2, restrict the evaporation of dry cleaning fluids. 3, restrict lighter fluid for starting barbecues. 4, reduce wood-burning stoves. So there's down nitrogen oxide, particulate matter, VOx, and carbon monoxide. And 5, reduce bakeries. Bakeries produce a lot of off-gassing. So cars have lots of emissions of nitrogen oxides and volatile organic compounds. So lower auto use, restrict driving, more mass transit, HOV lanes. The Clean Air Act Amendment in 90 and 95 established a free market to reduce sulfur oxides and they established this provision to buy and sell allowances. So essentially, you're releasing sulfur and you want to produce more output than your allowances allow. You want to up your energy production. Well, you have to buy those credits from another company. If you're producing less and you have extra credits, you can sell them and make a profit. Allowances reduce every year, so hopefully we get closer and closer. Ozone, we looked at tropospheric ground level pollution, so now we're going to take a look at the stratosphere. So this is that ozone layer that has the hole in it that we like to talk about. So sun energy, UV, light, infrared, most early organisms had to live in the water because it protected them from ultraviolet, because ultraviolet can cause mutations or death. UVA passes through the atmosphere, and there's not much absorption, and that's our lead causing of skin cancer. But UVB and UVC can cause damage, but 99% of that is absorbed by ozone. Stratospheric ozone is O3, which has a different function, a critically important different function than tropospheric, that ground level pollutant. So here's what's the reactions for ozone. So you have oxygen gas plus UVC, which is going to give you 2 free oxygen atoms. This only happens to a small fraction of oxygen, because mostly we have O2. And then that O2 plus an oxygen becomes O3. When we look at the breakdown, we look at ozone plus either UVB or UVC, which forms oxygen gas and a single oxygen molecule. It may recombine or it maintains a steady state, but the thing that's important is only ozone absorbs UVB, so it really protects the Earth. UVC is in both reactions. UVA just carries on, but UVB is a key part of this breakdown of ozone. Certain chemicals can break down the ozone, particularly chlorine. So chemical catalysts can break down ozone. Chlorine is our main one. It's the main major anthropogenic source is CFCs. Okay, so we have our chlorofluorocarbons. They're used in refrigerators, air conditioner, propellants. Chlorofluorocarbons are stable, inert, non-toxic, and non-flammable, so they were a great thing for us to use. But it does not change when escaped. There's 2 steps that occur. One is that ozone combines with chlorine to form that ClO plus O2, and then in step 2, that ClO that was formed combines again with oxygen to form Cl and O2, and so then that Cl is propagated again, so then it can join again with the ozone. So these chlorines, these CFCs, can destroy as many as 100,000 ozone molecules before they even leave the stratosphere. That's a pretty big deal. We want to have that ozone in the stratosphere to protect us, and so we don't want it to go away. This depletion of the ozone layer is significant. Like I've been saying, in the late 70s, we noticed that ozone depletion was going on. It was the greatest of the poles. This ozone hole got a lot of publicity. It severely reduced the ozone over Antarctica. You can see in the diagrams there, that ozone hole. Cold weather allows more chlorine to form, which catalyzes more breakdown. The warmer temperatures slow down the destruction, so the colder temperatures is accelerating it. When the ozone level goes down, we increase our UVB rays. They're increased now by 4%, which is harmful to cells and harmful to photosynthesis, which will decrease. It increases cancer. And in 1986, there was a big meeting in Montreal, which seemed overwhelming. What are we going to do about this problem? And in 1987, the Montreal Protocol was signed, and that's a big deal. It was a lot of countries, 24 nations signed, and then we made a few amendments, and 180 countries signed. But it was concrete steps to reduce chlorofluorocarbon productions by 50% by the year 2000. It finally put the global biosphere over economics, and 180 countries are a part of it, and elimination of CFC products. Right now, chlorine is 5 parts per billion, and we're looking to get it down to 1 part per billion by 2010.